let's move on to Lean. Okay, so here I am where I finished yesterday. And if you go to github.com/codespaces, if this is what you were using yesterday, you too can be where you were yesterday. For those of you who installed Lean on your computers, you can just open up Lean again. But let me model what you're doing if you're using Codespaces like I am. So you find this webpage that lists all of your existing code spaces, and you click on the one with the funny name that you were using yesterday. And while I'm at it, I might as well rename it to something like, you know, that I will remember, like Simon's 2025 main workspace or whatever, just so that I know what it means, but this is optional. Okay. Is that big enough? Okay, and now I'm going to click on it. And that will pull up my code space from yesterday. And I'll give it a minute. Okay, and one more, so this is really tiny, let me make it bigger. One more thing that I'll need to do, and that you'll probably need to do too, is to update with anything that I had changed last night, because I added a few tweaks to the exercises. So click on these three dots on the left to open up the terminal and press New Terminal. And then you'll need to type git pull. And these words here will pull the changes I made last night to update the exercises slightly. So when you've typed git pull, you then press enter. This is what Filippo demonstrated at the end of yesterday. And it's going to consult and find the things I modified since yesterday. And then once that's done, you can close your terminal and hopefully be ready to go. And my info view is still not ready to go yet. Maybe I should keep track of what's going on here. Maybe yours is working. If so, great. If not.
Do you have a local version you could open?
I do, but I mean, we ought to eat our own dog food, I think, and make sure that, you know, whatever solution we're recommending for the class also works for us. So just giving it a minute. I've got these yellow bars. When the yellow bars clear, that's when I'll be able to start working on Lean. And I'm in the geometry folder. So in geometry, just like in number theory and in real analysis, we've got multiple files. I'm in the first one where we do real transformations of the plane. Okay. While I wait for my yellow bars to clear, let me sort of show you the setup I've made to get started on this chapter that you were just reading. So problem one started by saying, you know, let's consider the function x maps to x plus a for some real number a. And we're studying this as a geometric operation on the real line. Great, okay. So when the red bars come, that's actually progress. You can press this restart file button. Okay. So we're studying the function x maps to x plus a. And I think the first piece of sort of invisible mathematics in this problem is that the function sending x to x plus a is described already as being a member of S sub a, the group of invertible transformations of the plane. But it's not like, we haven't already established that that's an invertible map, right? So really, before we go any further, to talk about this x maps to x plus a function, we ought to upgrade it to being an element of the symmetric group of the plane. And in order to do that, so maybe the first thing to know is that perm, standing for permutations, is the symmetric group. So maybe I'll keep notes. Maybe I'll keep notes on the other board.
I have one question. So,
please, yeah.
X, so how does Lean understand the type of X here in this would be written?
Excellent question. Let me write a couple of things, then I will return to it. So we have the function x maps to x plus a. And we are trying to consider this as an element of the permutation group of the plane, of the line, sorry. So this is perm R, it's the set of invertible linear transformations, sorry, invertible transformations, not necessarily linear, invertible functions from R to R. And so the components of this, you can see from this word where, and these pieces are, there are four components, namely there's a function, there's another function, which are supposed to be the two directions, and then there's two proofs, namely, the first function composed with the second function as the identity, and the second function composed with the first function as the identity. So those are the two conditions for two functions to be inverse. And here we know that we're supposed to be making, invertible linear, I keep saying linear, an invertible map from the real numbers to itself. So that answers Konstantin's question. How does it know what the x is here? Because it knows that in order to make, a permutation of the real line, that is an invertible map from the real line to itself, it needs as its first component a function from the reals to the reals. So if I hover over the x, it will have correctly inferred that this x here is supposed to be a real number. And that's because this function here has to end up being a function from the reals to the reals. So the four pieces we need are a function from the reals to the reals, another function from the reals to the reals, which will turn out to be the inverse of the first function, and then these two proofs. So I've started for you. I mean, I know what the inverse is supposed to be. The inverse of adding A is subtracting A. And, almost, at the first sentence of the exercise, we need to fill in these two proofs, which, as you can see, are that the x minus a function is left inverse to the x plus a function. And
does it know that a is a real number at this point?
It does, because I told it so.
Ah.
Yep. Good question, but yes. And then the other one is to show that x minus a is right inverse to x plus a. So before I can even say, like they do in that first sentence, consider the transformation x, x maps to x plus a of the real line, I need to check the package of being an invertible function in this way. Alex, did you have a question?
There's a question.
Oh, sorry, yeah, please.
Sorry. So does a being a real number there, does that automatically set the x to be a real number? Is that why you don't have to?
So I think it also needs to know, maybe it would, but I think it has the extra piece of information here that we're constructing a permutation of the real line. So a permutation of the real line is a function from the reals to the reals equipped with an inverse.
Okay,
and so it also has this extra r here to help it out as well. But if I wanted to be more explicit, I could say fun x of type reals, for example, and that would help me visually, even if I wasn't sure what Lean was doing. Yes, please.
What is a brief?
A brief, good question. So for technical reasons, I'm using a brief rather than def, which you may have seen yesterday. A brief and def have very slight technical differences, but I mean, you can think of it as being the same thing as def. Yeah.
Okay, so you're not defining the function that fits.
Yes, I am defining a permutation of the reals. And the components of this definition are fourfold, namely the two functions and the two proofs of left and right.
You must use the two fun as the actual function you're defining.
You
like
must.
This is some, like,
yeah. And let me show you how you would come up with that. If I knew I wanted to define such a function, and I didn't know what the pieces were, this is quite a useful trick. So you can press an underscore, and I get this light bulb here, this blue light bulb, and I press generate a skeleton, and it tells me what the four pieces are. So this is a very useful trick. If you have to construct an object and you don't know what the four pieces, what the various pieces of that object are, Lean can tell you because it knows what a permutation is supposed to consist of.
That's the point. If you click through the definition of perm, then they can see where those words are defined.
So I could do it that way, although I think I'd have to go back several layers to see all the pieces of information. So you can see a permutation is an equivalence, where an equivalence is a bijection, but yeah, I mean, after a couple of steps, I get to the same thing. Yep.
Sorry, and could you make it just a little bit larger?
Yep. Is that one getting to a reasonable size?
Yeah, that's good.
Okay, good.
Sorry, can you repeat the trick again?
Yeah, sure. So let's say I know that I have to construct an element of the permutation group of the reals and I don't know what it's supposed to be, I write colon equals underscore. This brings up this blue pop-up. I click on the blue question mark pop-up and I click generate a skeleton. And at that point, I'm told what the various pieces are.
So you have to be able to write down a formula for the inverse as well. So I can imagine, I know functions that are invertible, but I don't know a form that have a formula, but I don't know a formula for the inverse.
Yeah. So if you, in that case, I mean, you can, you can produce a proof that it must be bijective. Like there are fancier ways of making it that are not requiring explicitly writing down the inverse in this way. Yeah, for example. So you would have a existence theorem, that you would appeal to in that case. But let's do it the easy way to start with. Yeah. What was that?
Can you repeat the question?
Yeah, so sometimes because you've given a proof of it that there must exist an inverse, but you haven't shown what it is. So if you have a function which is injective and surjective, then it must have an inverse, but you require the axiom of choice or something like that to get exactly what the inverse is. So yeah, there are ways of making an element of the permutation group of the reals that are not this explicit form, but I think we'll stick to the explicit form for this lecture.
X to the 5th plus X, for example.
Sure, yes, quite so. So here we are. We have started off, I gave you a little bit of help because I told you what the inverse is supposed to be, but we now have two proofs to fill in, namely that X minus A is right inverse and left inverse to X plus A. And these are pretty easy, but I want to demonstrate them just as like a example of how to start, pretty easy lean proofs from first principles. So yesterday, I think Alex and maybe also Antoine explained the use of this unfold tactic for a definition you haven't seen before. We haven't seen this function dot left inverse definition before, even though we can maybe guess what it is. So I might like to write unfold function dot left inverse to see what I'm playing with. And it's pretty plausible. So it's saying I need to establish for every real number x that if I apply the x maps to x minus a function, after applying the x maps to x plus a function to x, then I get back to x. So, I mean, a lot of symbols there, but it seems plausible. For these lectures, I'm actually going to suggest using a variant of unfold called dsimp. So dsimp is a lot like unfold, but it also takes apart sort of silly bits of notation like the function application. So if I decide instead to do this dsimp rather than this unfold, it will also take apart this application of x maps to x minus a to the application of x maps to x plus a. So that's my preferred tactic for this kind of task. You can see that when I do it with dsimp instead, I immediately simplify down to having to prove that for all x, x plus a minus a equals x, which is really what's going on underneath all of that.
Is there any reason why we should use unfold instead of dsimp?
So dsimp will generally do a little bit more. Like as you can see, it also sort of unfolds notations and function applications and things like that. So if you're really perplexed by something and digging into exactly what's going on, if you're debugging sort of thing, you might prefer to use unfold. But personally, I generally use dsimp for that reason. Yes?
Why do you add bracket for dsimp?
Just who knows? Just for unfold, you don't have brackets. For dsimp, you do. Ask the gods of the library. I don't know.
In general, what is square bracket? What's this?
Square brackets usually allow you to provide a list of things. So here, for example, if I had several definitions appearing, as we'll see later on, and I want to take all of these definitions apart at once, I could have a list of different definitions and provide them in this square bracketed situation. In this case, there's only one thing in our list, but the square brackets allow you, in a way that can be parsed easily by Lean, to provide a whole list of things.
how did you know that you need to write function left inverse, like from the left in, like notationally, it's not clear. How do you do that there?
Oh, you mean because, well, because there was a left inverse appearing in the thing I had to prove.
The goal.
Yeah.
Okay.
Yeah, so I saw that I had to prove a statement about it being left inverse, and I was like, okay, what does that even mean? Let's ask Lean. So I took, yeah, good question. So I looked at what I had to prove, and I saw that this was what I had to prove, and so I said, let's take apart that definition, and that's what's left. So I have to prove now a statement that looks a lot more like what we were doing, for example, in real analysis like yesterday, although probably easier than those, namely a for all statement for all x, x plus a and minus x equals x. Any questions further than that at this point? Okay, so yesterday we saw some for all statements. What tactic do we use when we see a for all in the goal? Intro. So let me say intro x. By the way, I don't know if we fully explored this point yesterday, but you get to name it at the point where you say x. So if I wanted, I could have said intro y, and then it would have made the goal to prove that y plus a minus a equals y. I could have called it intro Heather, and you can see what happens. So I'm using x, but it will name things appropriately when you enter them. And now, so I'm not sure if we specifically talked yesterday about sort of algebraic manipulation of different kinds. This tactic linarith did appear in Alex's talk, but this is easier than that kind of thing, and I'm going to show you a lighter weight tactic for this situation. In this case, all we need to do is, some addition and subtraction. So there is I'm going to sort of maybe organize my tactics into three. So there's the pure logic tactics, which I'm going to keep track of over here. And then there's the sort of two other classes of tactics, so that I'll keep track of over here. So for sort of algebra, broadly speaking, / computation, I'm going to keep track of tactics in this column. And this is what I would call sort of lean convenience. It's a stupid name, but that'll be my three classes. So what I need now is a tactic that knows the rules of, either sort of additive abelian groups or possibly, commutative rings or something like that, that can just say, according to the axioms of the algebraic structure I'm working in, when you add something and then subtract it, you get back to where you were. So the tactic I use most in this category is ring, which knows the rules of commutative rings. And if I type ring here, it establishes to its satisfaction that x plus a minus a equals x. And
why didn't you have to introduce a?
It already knows about a from back here. So already at the start of the problem, we're given this a that's available, and that comes from the setup of the whole task. Okay, so see if you can fill in the right inverse proof.
Yes, thanks.
I think some people didn't hear the last thing I said, which is that your task now is to do the proof of right inverse. So I saw a number of people start by seeing that the words right inverse appear in the goal. And so quite rightly, their first idea was that we're going to take apart the right inverse definition. So many people got this far. And then the question is, now we've got a goal which is still expressed in terms of left inverse. So clearly what that means is that if you look in the library at where right inverse is defined, they've taken the quick definition and said that being, A being right inverse to B is defined to mean that B is left inverse to A. So that's fine, but it means that, just unfolding the definition of right inverse doesn't take us very far, unless we also unfold at the same time the definition of left inverse. So when I do that, I get down to a task that I can solve in the way we were studying before. Okay, and then having got as far as this, we have a for all in our goal. Anyone want to explain what I should do next? Intro. And now what should I do after this? Anyone?
Ring.
Great, okay. Good, so I've gotten to the end. I've gotten to halfway through the second sentence of exercise 1, which is great. Okay, let's move on to the next part of exercise 1. So, oh, please, yeah.
I think some of you noticed that like you don't need at least I'm not mistaken that you don't need this left inverse part.
So in fact, yes. So you never need the desimp lines. It always works without it. So this is purely for your understanding. Never is maybe too strong. I think there are some cases where you maybe do need it, but usually these unfoldings of definitions are purely for your benefit and not for Lean. So I like to do them, especially when people are starting, but I can just entirely remove them. Yeah. No, so this is a function from x to x plus a. So it's a function from the reals to the reals.
The first one is a function for the reals.
Oh, you mean that this takes in an a and gives me a permutation? Yeah, yeah, yep.
You've got a function
Yep.
from the real numbers to perm.
Yep.
And then you have a function from R.
That's right. Yep.
So now we go down the way and you say, well, I have to introduce the x, the
Mhm.
domain of the function from R to R.
Yep.
But I don't have to introduce the x,
Mhm.
which is the element, the domain of the function from R to perm R.
So it's a matter of syntax. So I could have said, for all a, I have a permutation. And if I wanted to do it that way, then I would have needed to start with intro a, and then I could have said exact, and then all of this business here. So this works. So if I say for all a, I have a permutation, then to get rid of the for all, I need to intro the a. So it's just a matter of whether it somehow comes before the colon or after the colon. Yep.
I guess I'm trying to ask what's the difference between those two, add right and func? Somehow func doesn't do that, but add right.
Yeah, I mean, as you can imagine, different ones are more convenient in different contexts, and so the keywords are set up differently. I think that's all there is to it. Okay, so, oh, thank you, yes. Okay, so let's move on. So the next task was to prove that this transformation of the real numbers we've defined, add right R, has the property that for any two real numbers a, sorry, for any x and y, alpha of x minus alpha of y equals x minus y. That was the next sentence in the exercise. Oh, I wrote it backwards. It was to prove that x minus y equals alpha of a minus alpha of x minus alpha of y. So this was the next sentence in the exercise. Let's see if we can establish that. So if for some given real number a, alpha is this element of the permutation group that we just defined, then let's show that it has the property stated. Okay, so I've set this exercise up. I've said, suppose I've got a real number a, and I define alpha to be the object we just defined, the add right operation on the real numbers, where we're adding right by a, to show that for all x and y, x minus y is alpha of x minus alpha of y. Any questions about the statement of this example? Okay, great. So this is a little bit different. We've got this weird let thing in the in the goal as well. Good news is that our old friend dsimp handles this kind of thing. So let's just hit dsimp to start with. And you can see this simplifies down to the task of proving sort of what we would think it is, namely for all x and y, x minus y is x plus a minus y plus a. Yes?
So I don't understand because alpha is actually some kind of composite structure, right? But you treat it like a function.
That is a very good question. So
I was wondering how does it go?
that's an excellent question. So alpha here, you're quite right, it's an element of the permutation group of the real numbers, but it is being applied to x. And there's some implicit coercion given that alpha is a function-like object. And although it's not showing up until you dig into the details in this way, you're quite right that under the hood, it's seeing that this element of the permutation group of R can, in particular, be considered as a function from the reals to the reals. So there's something being hidden from you there. Good observation. Other questions about the statement here? Okay, so I hit it with my simplification, and maybe this is a good time to mention one interesting thing. So you can see there's no parentheses around the x plus a. That's because by default, lean parenthesizes to the left. So if there's an operation like a plus and an operation like a minus, it sort of implicitly puts parentheses there. And if you ever forget about lean's sort of grouping convention, you can hover, for example, and you can see that when I hover here, it hovers over the x plus a, and if I hover further right, for example, over the y, it hovers over the whole group that the minus is capturing. So if you ever forget about the parenthesization convention and are confused by the fact that x plus a doesn't have parentheses, you can do this hovering trick to see what is being captured and see that implicitly the x plus a is being parenthesized. Okay, so take a minute, see if you can solve this exercise. So let's solve this problem. I have a for all, so I might as well write intro x. And as you can see at that point, I still have a for all. So I might as well keep going, intro the x and the y at the same time. And now I've got a ring-like task. I want to cancel the plus a's to get that x plus a minus y plus a is x plus a. That's a task for ring. So there goes that exercise. Any questions so far? Yes, please.
So this doesn't work if you don't do descend.
Interesting observation. Yes, you're quite right, it doesn't. Yeah, okay. Okay, so already, a first counterexample to what I told you that usually descend is not needed. In this case, it is. Other observations? Yes.
We are stuck just because whenever we tried, the group tactic still works. Here it doesn't work.
I mean, let's not talk about the group tactic. I think it's not as sort of robust as like the really core ones like ring. Okay.
Okay, so
Yeah.
you should always try to do the...
Well, we can talk about this later, but I think I won't be using that tactic at all. So let's just leave it. In the back, yes.
Why are we punctuating that and the for all statement, but not descend and show and ring?
I actually didn't catch that, sorry.
Why are we punctuating the first two lines after example?
I'm sorry, I can't hear you at all.
Why are there 4 spaces or?
Oh, I see. So this is totally unnecessary, but it is the convention in people who write for Mathlib, like I do, that when you are writing the statement of an exercise, the subsequent lines of the statement get indented by 4 to visually distinguish it from the proof, which is indented by 2. This is totally convention. Other questions? Maxine, maybe?
Just wondering if there's a way to know that a certain structure will have implicit conversion.
Yes, so I think in this case we can type #synth fun like perm real. Maybe it's not quite like that. Let's see, maybe I need to provide it with more information, maybe from the reals to the reals. Yeah, so it has synthesized that there is a coercion from the permutations of the reals to the functions from the reals to the reals, but this is really very advanced. Yeah. Other questions? Okay, so let us continue. So we are now on to sentence 3. Under the transformation alpha, the segment of the line from x to y has the same length and same direction, blah, 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 and such a transformation is called a translation. So now we're setting up this T, the set of permutations of the reals, such that this property here is satisfied. So I have made the definition an element alpha of the permutation group of the reals, such that for any x and y this property holds, is called a translation. So this is a def. So I've said, I define a permutation of the reals to be a translation if for all x and y, alpha of x minus alpha of y equals x minus y. So this is a definition. Any questions about the definition that I just made? Yes.
Maybe slightly off-topic question, but can one easily translate this to RD?
You mean like higher dimensions and
Yeah.
stuff? So if we get through the reals, you'll see the next file is on the complexes.
Okay.
But so far, like you're quite right. There's nothing that would stop me from putting like, I don't know, like you know, the p-adic numbers or something here. Like you know, I've been working in the.
Write somewhere like there RD, and then the definition will also.
So you would have to write it as like, I think fin d to the reals, because that's how you write. That's how you write RD in lean. But yes, in principle, there's, you know, in principle, I've used very little so far that really requires the reals. It probably work for any like additive abelian group or something. Other questions? Okay, so I have defined a translation to be a permutation of the reals with this property. And now we're on to sort of the main point of exercise 1, to check that the set of translations forms a subgroup of the permutations of the reals. So this is sort of the really interesting part of exercise 1. So I could have done this in the same way as before if I wanted to see what the pieces of the subgroup definition are. Let me do that. So I use this, I wait for my little blue pop-up to turn up, and it tells me the pieces of being a subgroup. That's how I got this. So what are they? I have to provide the carrier, which is the underlying set. So it's the set of alpha, the set of permutations of R called alpha, which are translations. And then I have 3 tasks. So if I hover over the first one, I have to show that the product of 2 things in my set belongs to my set. The second thing is to show that 1 belongs to the set, 1 being the identity permutation. And the third task is to prove that if you have a permutation, then its inverse is also in this. So if I have a permutation which is a translation, then its inverse is also in the set. Any questions about this and how it relates to the definition of subgroup you learned in school? Okay. So here I am with the first task. I have to prove for any 2 permutations A and B, if A is in the set of translations and B is in the set of translations, then A times B, which it is correctly interpreting to mean the composition of A and B, also is in the set of translations. Any suggestions about how I should start here?
Which way is the composition bad?
It will tell us, you know, I confidently expect that it will tell us later on. I am not sure, but I'm sure it will tell us. Yeah. I think it's B composed with A. Yeah.
Should introduce them?
I would do something even before that. Well, actually, no, you're right. Let's do that. So let's introduce them. Let's call them alpha and beta. Okay. Okay. What else should I do at this stage? Why not?
Oh, yeah, okay.
I was calling it alpha. I was calling it alpha before. Yeah. So I think I'm going to use Greek letters for my transformations of the plane. Okay. Any ideas about what I should do now? That what are real numbers? Well, they're not, right? They're permutations of the real numbers. Yep. Any suggestions for what else I might do at this stage? Desimp. Okay. Yeah, okay. So, all right. So let's unfold the definitions. You can see that, you know, it got rid of that membership of a set business and translated down to the essentials, namely, if alpha and beta are translations, then alpha times beta is a translation. I could even probably desimp further, right? Any suggestions about how I could unfold any further definitions here? Okay, let's further take apart the is translation part, and now I have to prove. If I know for all x and y that alpha of x minus alpha of y is x minus y, and if I know for all x and y that beta of x minus beta of y is x minus y, then I have to prove that for all x and y, and now we see the order of the composition, alpha of beta of x minus alpha of beta y is x minus y. So that was a lot of unfolding at once, but now we fully understand what we have to do. So maybe, in fact, I'll save that for later. We can come back to that part and just keep it as is translation for now. What else could I do on the problem as it stands? Great. Quite so. So looking again at our list of tactics from yesterday, when you have an implication symbol in the goal, you want to use intro on it. So let's introduce these two hypotheses. Okay. And now I have two hypotheses, that alpha is a translation and beta is a translation. I want to show that alpha times beta is a translation. And now, I mean, probably now is a good time to do all that desimping. But since things have moved around, if I type desimp, it only attacks the goal. I want it to attack these two hypotheses, so I can specify that I want it to desimp in all of the different places. So this syntax here says apply that simplification both at H alpha and H beta and in the goal. And now this is starting to look kind of promising. So I have two known facts, one about alpha, one about beta. I want to show a fact about the goal. Okay. So let's see.
So we introduced the X and Y, right?
Quite, yes. So I have a for all in the goal. So now I need to bring in some X and Y, some real numbers. Okay. So I guess that people probably got to this stage when they were solving exercises on paper. Did anyone, when they were solving exercises on paper, think about this particular task and what we would do now?
We need to do the hypotheses.
Okay. Yep. Maybe show of hands who felt like they solved this exercise on paper back in the first 20 minutes. Okay, great. Yeah, so that's quite right. We probably want to use this hypothesis here to change the alpha of beta of x minus alpha of beta of y into, so what would it turn into when we use this fact? Quite. So we can use this rewrite tactic. I'm not sure if anyone has showed you this before, but rewrite takes an equality or possibly an equality with a for all in front of it, and it looks for places where it would match. So here it sees that alpha of beta of x minus alpha of beta of y matches the form of this quantified equality here, and it makes the appropriate transformation. So if I rewrite H alpha, it turns the alpha of beta of x minus alpha of beta of y into beta of x minus beta of y. And I'm going to add that to our list of just sort of what I'm calling lean convenience tactics. And now I've got to show that beta of x minus beta of y is x minus y. Any suggestions? Great. And we have done this part. Okay, so it is coffee break time, and I have been asked to tell you that today there are multiple events happening, and so we want to keep to this room as much as possible. So go out and get your coffee, but then if you can come back and have your coffee break in here, Simons would be grateful to us. So get your coffee, come back in here, and we will pick up the lecture again at, I guess, 11 o'clock. In the meantime, I mean, I think you understand the basic gist of what's happening now, so feel free to advance further in the geometry exercises if you feel like it. Let me take a minute now and do the first exercise that needs an external piece of information. I'm going to try over the course of the next hour to get through each of these pieces here where a new tool is introduced. So let me demonstrate this piece where we need to use the rewrite question mark. That was it this one here? Oh, sorry. Sorry, this is, I want the internet. Okay. So that was this part here where I wanted to use the invmem. So give me a minute, as you were. So let me just demonstrate the one that I skipped before. So I wanted to demonstrate how to use rewrite question mark if needed for this exercise here. So here we are in the inverse exercise, pretty similar to the multiplication exercise. I have an alpha, I simplify some stuff, and now I have to prove that if alpha is a translation, then so is alpha inverse. So use intro to get my translation property for alpha, try to deduce it for alpha inverse. Let's desimp a bit more to get rid of the is translation definition. translation at H alpha and the goal. Okay, so here I am sort of where we, and now intro X and Y. And I think the place where people started sort of, okay, so most people got as far, I think, as saying, let's apply H alpha to turn this side into alpha of X of Y minus alpha of alpha inverse of X minus alpha of alpha inverse of Y. So to do that, we need to use this H alpha in the opposite direction, turning this into something that has the alpha applied in both cases. So rewrite backwards by H alpha. And now we are in the position of needing to show that alpha of alpha inverse of X equals X, and that alpha of alpha inverse of Y is equal to Y. And this is where we need to use the first hint that I was giving before about this rewrite question mark tactic. So what does the rewrite question mark tactic do? It searches the library for lemmas that could be relevant. I'm doing that here because I know that somewhere in the library they clearly have something that will turn, you know, like any sensible library will have a lemma that allows me to turn alpha of alpha inverse of X into X. And so I know it's just a search problem to find whatever that statement is in the library. So rewrite question mark finds it on the third try. It's the third lemma. It comes up with this perm apply in self. So I click that, and you can see that this now is the lemma where before I have a alpha of alpha inverse of X, and after I just have X. So that is exactly the lemma I wanted. You can also hover over the statement of the lemma and see it precisely says, if F is a permutation of some type and X is in that type, then applying the inverse and then applying the original one gets me back to X. So this is exactly the lemma you want here. And I found it by searching the library using this rewrite question mark tactic that I was suggesting. And so that got me part of the way there. It got rid of the alpha of alpha inverse on the X, and now I want to do it one more time on the Y to finish off the exercise. And then this exercise is done. Yes, please. Yep.
Do you really have to type it twice, or is there a short? Yeah.
So I could have combined them into a single line, for example. Another thing I could have done, although I'm not sure if it works, some people had trouble with this, is sometimes you can type repeat. Did that work? Yeah, that works. Okay. Yeah. And then there are other variants as well, but yeah, I think. Yeah.
And the at sign on the beginning. When
The at. So the at is a sort of artifact of the library search procedure. It is usually completely meaningless, but not always. Okay. Okay. So I think that's all for the first trick that I was demonstrating, the hints. Okay, so now I think until you get down to this question here, you will not need anything new. And then when you get a little bit further, these are the two things you'll need at the next step. So I'll let people keep working. Oh, yes, please.
Instead of this repeat, you can also use sim only. And whenever, if you use sim only, whenever there's an instance we can use,
yep,
it's also works.
That's true. So simp simp does many things, but in particular, simp can be thought of as a variant of rewrite. So I think I will not be talking too much about this simp tactic in my talk. You may get to hear about it in Antoine or Alex's talk later on, if you're not, I'm not sure. But yeah, simp, think of it as a variant of rewrite. And in particular, it differs from rewrite in applying something as many times as it can, rather than just the once. Okay, so onward and upward. So I'd like to take a moment and demonstrate a couple of the hints for another of my pieces. So this linear combination tactic comes up in my solutions for the first time in assessing, I think, this one here. Okay. So if you have an element of our new translation subgroup, and it fixes 0 to show that it actually is the adding A operation. So we need to use 2 new tactics for this one. The, not the solutions, we need to use, I told you to use the X tactic and the linear combination tactic. So let's demonstrate that. The X tactic stands for extensionality. Yes, I do. Thank you. So X stands for, maybe yeah, so rewrite and rewrite question mark, okay. So X stands for extensionality. And this is a word beloved by computer scientists that I had never heard, and still I started messing around with this kind of thing. So X for extend with an S, extensionality. This is the statement, you know, well known to all of you without realizing that it's actually an axiom, that 2 functions are equal if for all inputs they are equal, you know, on those inputs. So we want to show the equality of these 2 functions, and we're going to say, okay, take an X and let's show that they evaluate to the same thing on X. So this is function extensionality, and I type X to X for it. And now, let's see, so dsimp will take us a certain distance. I need to show that alpha of X is X plus A, given that alpha of 0 is A, and that alpha is in the translation subgroup. Maybe I'll also remind myself what being in the translation subgroup means. Okay, well, it means that it is a translation. Let's unfold the definition of being a translation. Okay, so this looks more like it. I know that for all X and Y, alpha of X minus alpha of Y is X minus Y. And I probably want to apply this to what values? Did anyone figure this out? What values is this useful for in this case? Y is 0 and X is X, yeah. So this is the setting we were in during Alex's lecture yesterday. We have a for all in a hypothesis, and we want to fill in some values. So let me fill in some values in our hypothesis. So I'll call it H. The fact that you can, that you get from applying our known fact H alpha to the values X and 0. And that tells me, just as I wanted, that alpha of X minus alpha of 0 is X minus 0. So at this stage, this piece plus this should be what I need here. And I might as well make it even simpler so I can directly change the alpha of 0 into an A if I want to clean up H. So rewrite little h at big H. Okay, and now I'm in a position where I know that alpha of X minus A is X minus 0, and I want to move the A onto this side and cancel the 0 to get that alpha of X is X plus A. So this is where I want to use the second tactic I mentioned in the hints, linear combination. Let me demonstrate the use first, and then we can talk about what it's doing. Linear combination H. So can I, if I write on this board here, will people be able to follow? Can people see this board well enough for me to write there? So before I typed linear combination, I had a hypothesis, capital H, that alpha of X minus A is X minus 0. And I had a goal of showing that alpha of X is X plus A. And what I want to, so this is very much in the spirit of the ring tactic that we were using before, and that most of the work is being done by the axioms of a commutative ring, but it is outside the scope of the ring tactic in its pure form, because ring does not take account of hypotheses. I want to say if you use the ring axioms on H and on the goal, you can turn them into each other. So this is slightly beyond the scope of the ring tactic in its original form. So what I want to do instead is I want to say, if I bring everything onto the left-hand side in both of these, then I can ring normalize them to the same thing. So let me explain what I mean by that. So a sort of modified problem, which is sort of constructed under the hood by the linear combination tactic, is given that alpha of x minus a minus x minus 0 is 0, to prove that alpha of x minus x plus a is 0. So when you say linear combination H, it sets up this modified problem, and then it ring normalizes this expression and this expression and checks that you get the same thing. So check this for yourself in your head. If you get rid of the 0, if you expand out the minus signs, in both cases you get alpha of x minus a. So that's what the linear combination tactic does. It's a light wrapper on top of the ring tactic, which allows you to invoke hypotheses in some combination. So I should say one more thing, which is that I am going to have you use, if you follow my advice, the linear combination tactic for now. But in Alex's talk on analysis yesterday, he was using even more advanced technique. He was using the linearith tactic, which doesn't require you to explain how the hypotheses combine together to get your goal. So I think that for beginners, it's often quite useful to explain to lean how the hypotheses combine to give what you want. But once you're more experienced, you can use the linearith tactic, which basically is running the simplex algorithm to find what combination of the hypotheses works, and then running linear combination. So there's a variance of sort of levels of generality, and I think sort of using this intermediate level of automation is quite useful for us for now. Any questions about this exercise? Maybe one more observation is that I could also have wrapped the rewrite step in. So I think this will just work if I say linear combination H plus H. So rather than rewriting by little h. So now this is just saying, if I take the formal linear combination of little h plus big H and then move everything onto the left-hand side, that simplifies down to the goal. So this is how to make it one line shorter. And even one more thing that I could do to make it even shorter if I wanted to, is that rather than writing H, I could just write the thing I typed to get H. So this is probably like, is this as short as it could be yet? I guess maybe I still could get rid of the unfolding of the definitions. Can I get rid of this one? No, okay. So I think this is as short as it can be, but
linearith wouldn't work here, I suppose, right?
maybe that's right, yeah.
Question?
Please, yeah.
In what sense is that big H plus little h being parsed? Like what type of?
So it would really just be forming like the sum of the left-hand sides equals the sum of the right-hand sides. This doesn't even use the ring axioms. So like whenever you have an operation, a function of two variables, if you know that if you have two expressions which are equalities of things you want to put in as the first variables, another equality which is an equality of the things you want to put in as the second variables, then f of like a primed, sorry. Yeah, if in very high generality, if you know a equals a primed and b equals b primed, then f of a b equals f of a primed b primed. So you're not using like ring axioms or anything to do this kind of logic. This is, you know, this is really just in the sort of spectrum of pure logic.
So you're working in some polynomial expressions where alpha x, or
Yeah.
variables.
So the linear combination tactic to set up this modified problem, I claim it's not using very much. It's just using the fact that if you can prove it with the subtraction here, then you can move it onto the other side. And then the rest of the work is done by the ring tactic. You can even sort of divided into two pieces. So you can say linear combination norm colon equals skip, which means set up the modified problem, but don't actually run ring in the end. And you can see that this has set up what we send to ring to be checked in the end. And it turns out that what ring is being asked to check is this identity here. And the linear combination tactic has set up that it will solve the problem if we can establish this fact here. And you can even look, if you're interested, using this show term tactic at what is needed. So you can always look under the hood. Sometimes it's more instructive than others. But the linear combination tactic is a light wrapper on top of the ring automation, which forms a sort of, you know, somehow constructs a certain difference between the hypotheses and the goal, which is what you need to check about the algebra to ensure the deduction you're claiming is valid. So if that's, all too much for you, feel free to also just use linearith. That also works. If you want to think for now a little bit about where linearith is getting its information from, you can then stick to linear combination. Okay, so I think that will take you down with that information down to find the fixed point of alpha. So you've got a few more exercises that you can fill in. I'll give you a few minutes, and then let's see, I'll talk about the constructor tactic when it comes time to finding the fixed point of alpha, which will be the next point where you need some input. We have 3 minutes before lunchtime. Let's come back together and do the last of the next of these problems where I had indicated that you needed a bit of input. Let's do this problem where the constructor tactic appears for the first time. So we've come down to finding the fixed point of this alpha, which is a half turn. So let me unfold all the definitions. We have to show that two sets are equal. The first set is the set of real numbers x such that minus x plus a equals x. The second set is just the set a over 2. We want to show the equality of two sets. And maybe when you're teaching intro to proof to first or second year students, you've discussed how to show the equality of two sets. Anyone? Equality of two sets. How do you prove it?
Containment in two sets.
Oh, okay. Well, that's the textbook you follow. Anyone? Okay. So yeah. So sometimes you say you have to show subsets in both directions. I usually teach this in a slightly different way, and I say you have to show that x is in the first set if and only if x is in the second set. So yeah, I guess matter of choice. So let's take this approach I was saying, the sort of element-wise characterization of equality of sets. I introduce a variable, maybe I'll even call it y for a distinction, which says that, I've taken a real number y, and my task is to prove y is in the left set if and only if y is in the right set. Okay, so this is a new use of the extensionality tactic. We used it before on the equality of two functions. I'm showing you now that it can also be used for the equality of two sets. If you want to discuss with me over lunch, we can explain why in Lean a set is actually a function, and that therefore makes sense. And so we have to show the equality of these two sets by showing an if and only if about membership. Now, I told you that we would need to use the constructor tactic for the first time. The constructor tactic falls in this family of logic tactics, which specifically addresses one logical symbol. It handles if and only if. It also handles and, as you may later discover, in the goal. So if you have an if and only if in the goal, there are two tasks that you need to split it into, two implications, one in each direction, and that is what constructor figures out for you. So I think I won't even finish off this exercise for you because the rest should be doable with what you know already, but the setup for the problem uses the ext and the dsimp, and those are the new pieces.
Speak for the slash dot for itemization, because many people.
Oh, sure, yeah. So if for example, you have been using like Claude or ChatGPT, like Alex was yesterday, it may have suggested things involving these dots for you, and you can use them if you like. So these dots which are optional, allow you to sort of visually indicate in your proof which parts of the code pertain to which parts of the proof. So if you use dots, it then becomes very important that all lines after the dot get indented to match this position that the dot has sort of pushed you into. So if you have like a proof where you're using the dots, then everything will get indented 2 spaces. And the reason people like to do this, well, there's a couple of reasons. One is that you can see it sort of becomes visually clear. Construct your set 2 directions. Here's where the first direction proof is. Here's where the second direction proof is. So that's sort of a visual cue to your reader. And secondly, inside, so before the dot, you've got 2 things to prove, but inside the dot, you focused on just the first thing. So it cleans up your info view over here by hiding all of the other things that you'll have to come back to later and letting you sort of visually focus only on the thing you're working on. So totally optional, but a useful task if you want to use these sort of advanced stylistic tricks. Okay, so I think that's all for geometry. Good work, everyone. Let's go and have some lunch.
Thank you.